Good day. Welcome to another session in remote sensing and GIS. I am Dr. Raviraja. In previous classes, we have seen definitions of remote sensing and the types of data sets and the process of remote sensing. And in the process of remote sensing, we have seen till two steps. One is the source of energy, another one is the interaction with the atmosphere. The third step is the interaction with the target. We will continue from this one. Interaction with the target. Incident energy is represented with I and is being absorbed with the letter A, and T is the transmitted energy, and R is the reflected energy by the vegetation leaf. The figure shows this information. Radiation that is not absorbed or scattered in the atmosphere can reach and interact with the Earth's surface. There are three forms of interactions that can take place when energy strikes or is incident upon the Earth's surface. They are absorption, transmission, and reflection. Here, the proportions of each will depend on the wavelength of the energy and the material and condition of the feature. The amount of energy radiant onto or off of or through of a surface per unit time is called radiant flux phi and is measured in watts. The characteristics of the radiant flux and what happens to it as it interacts with the Earth's surface is of critical importance in remote sensing. By carefully monitoring the exact nature of the radiant flux in selective wavelengths and how it interacts with the target, it is possible to learn important information about the target. Various radiometric quantities have been identified that allow us to keep a careful record of the incident and existing radiant flux. So, we start with the simple radiation budget equation, which states that the total amount of radiant flux in specific wavelengths lambda incident to the terrain phi must be accounted by evaluating the amount of energy reflected from the surface rho lambda and the amount of energy absorbed by the surface alpha lambda and the amount of radiant energy transmitted to the surface tau lambda. So, the total radiant flux incident to the terrain phi I lambda is the summation of all these values, and it is important to note that these radiometric quantities are based on the amount of radiant energy incident to the surface from any angle in a hemisphere, that is the half of a sphere. Various radiometric quantities have been identified that allow us to keep a careful record of the incident and existing radiant flux. Okay, so these are the quantities: rho phi, rho lambda, tau lambda, and alpha lambda. Radiant energy must be conserved, and that is either returned by the reflection transmitted through a material or absorbed and transformed into some other form of energy. The net effect of absorption of radiation by most substances is that the energy is converted into heat, causing a subsequent rise in the substance's temperature. The first one is the hemispherical absorbance. It is the ratio of energy that is absorbed by the surface. So, which absorbed in a specific wavelength and radiant flux to the flux incident to the terrain. So, alpha lambda is the phi absorbed by the total phi incident wavelengths. Hemispherical transmittance is the ratio of the energy that is transmitted through the surface of the specific wavelengths lambda. Tau lambda as defined previously is equal to phi transmitted by the total incident flux. Hemispherical reflectance is the radio of energy that is reflected by the surface in a specific wavelength, of course, and the radiant flux incident to the terrain. So, rho lambda is the phi reflected by the phi incident radiant flux. These radiometric quantities are useful for producing general statements about the spectral reflectance, absorptions and transmittance. Characteristics of these terrain features, in fact, if we take the simple hemispherical reflectance equation and multiply it by 100, we obtain the expression for percentage of reflection. Similarly, in percentage of reflectance, in percentage of transmittance, in percentage of absorption. There are two general types of reflecting surfaces which interact with the electromagnetic radiation. Uh, those are specular and diffuse. Specular is nothing but from reflecting surface of a smooth, and diffuse is the reflecting surface of the rough surface. The Rayleigh criterion is used to determine the surface roughness with the respect to the radiation. Since we know h is the surface irregularity height measured in Armstrongs and lambda is the wavelength which is also measured in Armstrongs, then theta is the angle of incidence which is measured from the normal to the surface. In general, the Armstrong is the unit of length which is equal to 10 to the power of minus 10 meters, and if the measured wavelength lambda is less than the h, then the surface acts as a diffuse reflector. If it is greater than the h, then the surface is a specular, that is a smooth surface. For example, a sandy beach is smooth to longer wavelengths radio wave, but it is rough to the visible light. So, the surface is not only identified based on touch or visual identification, it must be identified as smooth or rough based on the wavelengths. So, the specular reflection occurs when the surface from which the radiation is reflected is essentially smooth, as we discussed earlier. That is, the average surface profile height is the several times smaller than the wavelength, then it should be taken as the smooth surface. If the surface has a large surface height variations compared to the size of wavelength of the incident energy, then the reflected rays go in many directions depending on the orientation of smaller reflecting surfaces. Here, the nature of the specular and diffusion reflection is shown in the figures. The first one is the ideal specular reflector, smooth reflector, that means, and is a ideal surface. That means angle of incidence is equal to the angle of reflection. But in general, which is not ideal surfaces are not exist, then a near perfect specular reflector is shown in the second diagram. But it is showing a small deviation along with the smaller reflections. In the second one is the ideal diffuse reflector, shows it is a Lambertian surface which is a hard surface or rough surface with equal distribution in all directions. But so the previous diagram, third diagram, shows the near perfect diffuse reflector in one direction which is giving high reflectance value. This diffuse reflection does not yield a mirror image, but instead produces a diffused radiation. Rough surfaces act like diffuse reflectors if any diffuse reflector reflects in such a manner so that the radiant flux leaving the surface is constant and for any angle of reflectance. Then the reflector is also called ideal diffuse reflector or a Lambertian surface, as I shown in the previous diagrams. This is an important topic and shows the spectral reflectance curve, which shows the relationship of electromagnetic spectrum with associate the percentage of reflectance for any given material. Here it shows the different materials. One is the vegetation curve, another one is the dry soil which is having only 5% of water, another one is the wet soil which is having 20% of water, third one is the turbid river water, finally clear lake water. It shows the reflectance value in y-axis and wavelength in the x-axis. The wavelength is going on starting with the blue band, green band, red band, another one is the near infrared band, finally short wave infrared band. So, you can observe the reflectance values of vegetation is higher in near infrared band. So, anyone want to research on vegetation areas, they can go for near infrared bands, so that they can know the values of the vegetations more carefully. Similarly, the dry soil reflectance values, wet soil reflectance values, river beds, clear water reflectance, you can all observe in the spectral reflectance curves. Here, once the object radiant energy is interacted with the object or area of interest, then it will reflect back into the satellite. Then it will again interact with the atmosphere. So, that is the interaction with the atmosphere again. The radiant flux reflected or emitted from the earth's surface or area of interest once again enters into the atmosphere, where it interacts with the various gases, water vapors and particulates. Thus, atmospheric scattering, absorption, reflection and refraction influence this particular radiant flux once again before the energy is recorded by the remote sensing system. Ideally, this radiant energy recorded by the camera or detector is a true function of the amount of radiance leaving the terrain at a specific solid angle. Unfortunately, other radiant energy may enter the field of view from various other paths like atmospheric interaction, solar irradiance, sky irradiance, scattering, etc., and introduce confounding noise into the remote sensing process. In the diagram, you can see the remote sensor is placed on the satellite and the solar irradiance is coming from the sun, and which is directly coming into the atmosphere, and there is diffuse the sky irradiance. Then it is reaches the object of interest, there multiple absorptions, scatterings are happening, and again it is reflecting back into the satellite, and it is while interacting with the atmosphere. Further, the light from the target outside the field of view of the sensor may be scattered into the field of view of sensor. This effect is known as adjacency effect. So, that the total radiance recorded by the sensor LS is equal to the radiance written from the area of interest LT. Unfortunately, both are not equal, because there are some additional radiance from different paths which may fall within the field of view of the sensor system. This is often called path radiance, which is denoted with LP. Thus, the total radiance recorded by the sensor becomes LS is equal to LT plus LP. After data is received by the satellite, this particular remote sense data may be collected using onboard aircraft remote sensing sensors, cameras, or based on applications. And this aircraft remote sensing system may also be referred to as a suborbital or airborne or aerial remote sensing system. This may be a satellite, or may be a drone, or maybe a unmanned aerial vehicle, maybe any other type of device can be there. The satellite remote sensing system may also be referred to as orbital or satellite airborne remote sensing system. Aircrafts and satellites are known as sensor platforms. Satellite remote sensing system may be referred as orbital or satellite airborne remote sensing system, and aircrafts or satellites are known as the sensor platforms. So, there is a difference between the platform and system. Data obtained during airborne remote sensing missions can be retrieved once the aircraft lands. It can be processed and delivered to the end user. However, data acquired from satellite platforms need to be electronically transmitted to the Earth, since the satellite continues to stay in orbit during its operational lifetime. The technologies designed to accomplish this can also be used by an aerial platform, or if the data can urgently needed on the surface. So, in transmission, reception and processing, there are three main options for transmitting data acquired by the satellite to the surface. The data can be directly transferred to the Earth if a ground station, or we can call it as a GRS, ground receiving station, is in the line of sight of satellite A. If this is not the case, the data can be recorded on board on the satellite B for transmission to the GRS at a later time. That means, if the satellite is not in line of sight with the Earth station, then we need to save the data, then we need to wait till the satellite comes in contact or in line of sight with the Earth station. or if the data is urgently needed, then the data can be relayed to the GRS through the tracking and delay data relay systems, TDRSS. So, in which it consists of series of communication satellites in geosynchronous orbit. The data are transmitted from one satellite to another until the satellite is in the vicinity or line of sight with the ground receiving station. These are the three ways we can transmit the data from satellite to the Earth surface. In India, ISRO operates one ground receiving station at Shadnagar, which is 55 kilometers away from Hyderabad, Andhra Pradesh. This Shadnagar covers all of India, Pakistan and Afghanistan, Bangladesh, Burma, Thailand and portions of Iran, Oman, Cambodia and Laos. The approximate vicinity of the Shadnagar GRS is shown in this particular figure. So, the data center which is placed in only one area, which is in Hyderabad, then it can receive the satellite data from any satellite which is in this particular vicinity. The data are received at the GRS is in a raw digital format. They may then, if required, be processed to correct systematic, geometric or atmospheric distortions to the imagery and be translated into a standardized image format. Here, the standard image format, most of the cases used is the tagged image photography, TIFF format, tagged image file format. Okay. In this particular format, GRS tags can be stored. So, most of the geospatialists will use this particular data format. The data are written to some form of storage medium such as tape, magnetic disk or CD. The data are typically archived at most receiving and processing stations, and full libraries of data are managed by the governing agencies as well as commercial companies responsible for each satellite or sensors. For the case of India, ISRO is maintaining a data center which is called NRSC, National Remote Sensing Center. This National Remote Sensing Center is responsible for maintaining and archiving the libraries of this particular data. So, interpretation final stage is the interpretation and analysis. Data alone cannot be used for decision making. It must be interpreted or analyzed before one can extract the information. The analysis of remotely sensed data is performed using a variety of image interpretation and processing techniques, which fall into two broad categories. One is the visual image interpretation, another one is the digital image processing. So, here both analog and digital image data allows the analyst to perform scientific visualizations defined as virtually exploring data and information in such a way as to gain understanding and insight into the data. Most of the fundamental elements of image interpretation are used in visual interpretation analysis, which includes size, shape, shadow and color or tone, parallax, pattern, texture, size, association. For example, if anybody want to use the satellite data to count the number of trees from a given satellite image, they need to understand how the tree can be visualized from the satellite. That means the top view of the tree. Top view of the tree is like a circular color, like since the crown of the tree looks like a circle, and the color and the shadow it can imprint in the image. So, that means you need to analyze the size, shape, color and shadow and texture of the trees. So, some trees may have a bunch of higher number of leaves, some may have lower number of trees based on the species of the trees. So, the human mind is amazingly adept at recognizing these complex elements in an image or a photograph, because we constantly process the profile view of the earth features every day and continuously process images in books and magazines and televisions. But the digital image processing needs, our computer needs these details. So, the significant advances in the digital image processing or computer processing of remote sensory data for scientific visualization and hypothesis testing, we can need to process the or fed the information into the system. For example, using the machine learning models. Nowadays, all the people are using machine learning models or deep learning models to identify and segment or analyze the data. It is commonly known that the human eye can discriminate only about 49 to 50 shades of gray when interpreting a grayscale image. But if the data is originally recorded with the 256 shades of gray, there may be more subtle information present in the image than the interpreter can extract visually. So then we need to go for a computer. A computer can analyze each of these data in an image using various digital image processing techniques, and further several mathematical operations on or among the images can be applied that can aid in information extraction and analysis. The major types of digital image processing include statistical and synthetical pattern recognitions. Here, so the digital image processing will help in many ways, from identifying different objects to segmenting different objects. So because it can identify many number of gray shades or color shades. Since the image is recorded in unsigned integer 8 format, then we have 2 bits 0 and 1, that means 2 power 8 is equal to 256. That is why they mention it as a 256 gray shades. If we use unsigned integer 16 format, which will be 2 to the power of 16, since many of the satellites nowadays are using unsigned integer 16 format for finding the various number of shades, so that it can identify or distinguish between the objects. Okay, I will stop with here now, and I will continue with the applications and limitations on ideal remote sensing system in the next class. Thank you.